Hello and welcome to a demonstration on how to determine algebraic forms of rational function graphs. Let's look at our first example. Here is the graph of a rational function. The asymptotes are dashed, so they are not part of the graph itself, but they do provide guidelines on the behavior of the function as we approach certain values. Now, it's important that we observe quite a few things from this graph. The vertical asymptotes, which I'll abbreviate VA, are located at x equal -2 and at x equal 3. The graph changes sign across both these asymptotes. There is an x-intercept at 1, 0, and the graph crosses the x-axis here. There is a horizontal asymptote, which I abbreviate HA, at y equals 0. The degree of the denominator is greater than the degree of the numerator. This is a conclusion that we may draw from the fact that the horizontal asymptote is located at y equals 0. There is also a y-intercept at the point 0, 1/2. Now, how can we use this information? Well, vertical asymptotes mean that the denominator happens to be 0, but the numerator is not 0. So this means that x plus 2 and x minus 3 are factors in the denominator. These will also not be factors in the numerator in a reduced form. Since there is a sign change across each of these vertical asymptotes, the multiplicity of the root has to be odd. Therefore, we have a factor of x plus 2 and a factor of x minus 3 in the denominator, and both of these factors will have a multiplicity that's odd. We'll pick the smallest multiplicity that's odd, which is 1, in order to keep the function relatively simple. We also know that the graph hits the x-axis at 1, so the x-intercept being at x equal 1 implies that x minus 1 is a factor in the numerator, and this is also not a factor in the denominator in the reduced form. For all three of these, we are actually using the factor theorem and the graphical interpretations of such behaviors. Now, when reduced, the rational function will have x minus 1 with odd multiplicity because the graph crosses the x-axis here. So right now, my template is going to be some value a, which we're going to figure out this value in just a second, times x minus 1, and then all of that is going to be divided by x plus 2 times x minus 3. The horizontal asymptote implies the denominator has a higher degree than the numerator. Our template already reflects this. Therefore, there are no additional changes that need to be made from this piece of information. But the y-intercept is what's going to allow us to determine the value of a. When I put 0 in, I should be getting 1/2 back from the function. So when I put 0 in, I end up with a over 6. And a over 6 reduces to 1/2 when a equals 3. So my rational function has the form 3 times x minus 1, and then all of that will be divided by the product of the factors x plus 2 and x minus 3. Our second example appears as what we see on the graph here. So take a minute to observe this graph and see if you can pick off the important information. From the graph, we observe there's a vertical asymptote at x equal 2, but in this case, there is also a hole in the graph at 115. What this means is that when I try to put 1 into this rational function, I do not have the point actually pair up. The reduced form of our rational function will output 15 when I put 1 in, but the original form, which is what I seek, will not have existence at this point. There is an x-intercept at -2, 0, and the graph will cross at this point. There is a horizontal asymptote at y equal -5. From here, we may conclude the degree of the numerator is equal to the degree of the denominator. And there is a y-intercept at 0, +5. So how can we use this information? Well, the vertical asymptote located at x equal 2 implies that x minus 2 is a factor of the denominator, and this is not going to be a factor of the numerator of the reduced form. It also has odd multiplicity because the graph changes sign across this asymptote. So right now my template appears as some polynomial p of x divided by x minus 2. The hole in the graph located at 115 implies that x minus 1 is a factor of both the numerator and the denominator. Additionally, the multiplicity of this factor is the same. It does not show up in the reduced form, but in the original form it will. So right now we have some number a, that we're going to figure out its value later, times x minus 1 times some polynomial q of x, and this is going to be divided by the product of factors x minus 1 times x minus 2. Again, the x minus 1 part is what gives us the hole in the graph. The x-intercept at -2, 0 implies that x plus 2 is in the numerator of our rational function, and it appears in the reduced form. It has odd multiplicity in the reduced form, and it is not a root of the denominator. Therefore, our template right now looks like a times x minus 1 times x plus 2 in the numerator, and then in the denominator, it will be x minus 1 times x minus 2. Now, the horizontal asymptote occurring at y equal -5 implies the degrees of the numerator and the denominator are equal. So when we look at our degree in the numerator, we have a degree 2. When we look at our degree in the denominator, we also have a degree 2. Therefore, the degrees currently are equal, and the ratio of the leading coefficients must be -5. So right now, we're going to put in -5 for a as an initial guess, if you will. Now, with our template, we have -5 times x minus 1 times x plus 2 in the numerator, and we have this divided by the product of the factors x minus 1 and x minus 2 in the denominator. Now we're going to test this using our y-intercept. When I put 0 in for x and I do the arithmetic, I end up with +5 as the output. Therefore, the y-intercept matches, and thus our template seems to match up with our behaviors. So our template at -5 times the factor x minus 1 times the factor x plus 2 in the numerator, divided by the product of the factors x minus 1 times x minus 2 in the denominator, this seems to be our rational function that matches our graph. Our next example appears as what we see here. So take a moment to study this graph and then determine where the behaviors match up so we can build an algebraic form for this rational function. We observe that we have a vertical asymptote at x equal 2. The graph changes sign across this asymptote. In this case, we have an oblique asymptote, or an OA, as it's abbreviated, at y equal x plus 7, and the graph does not intersect this asymptote. The degree of the numerator is greater than the degree of the denominator because of the presence of the oblique asymptote. We have x-intercepts at -3, 0 and -2, 0. We have a hole in the graph, and that's located at -1, -2/3. We also have a y-intercept at 0, -3. So we're going to put all of this information together to construct the algebraic form of our rational function. The vertical asymptote at x equal 2 implies that x minus 2 is a factor of the reduced form. X minus 2 does not cancel out, and it has odd multiplicity because the graph changes sign. So currently, right now, we have some polynomial p of x that we're going to figure out is going to be divided by the product of some other polynomial q of x times x minus 2. We have this q of x in here because we have more information that we're going to use. Now, the hole in the graph occurs at x equal -1, and this means that x plus 1 must be a factor of both the numerator and the denominator, and they must have equal multiplicities since the hole is not located on the x-axis. So right now, my template appears as x plus 1 times some polynomial p1 of x. We're going to figure out this form, and we're going to divide this by the product of the factors x plus 1. That's what's going to give us the hole. X minus 2, that's where my vertical asymptote is, also times some q1 polynomial that we're going to figure out what its form is as needed. Now, the x-intercepts are located at x equal -2 and x equal -2, or -3. This implies that x plus 2 and x plus 3 are roots of the numerator polynomial in the reduced form of the rational function, but they are not roots of the denominator polynomial. So these will not appear in the denominator. So right now, my numerator appears as some value a, which we'll figure out in a moment, times x plus 1 times x plus 2 times x plus 3. The denominator of our template has x plus 1, because that's where the hole is, x minus 2, that's where the vertical asymptote comes from, and some other q1 polynomial. So what we're going to do here is we're going to now use what we know about the oblique asymptote. The presence of the oblique asymptote says that the degree of the numerator must be bigger than the degree of the denominator. Now, in my current template, this is actually the case. So this q1 polynomial, we're simply going to drop. And the reason why we're going to drop this is because currently it's not needed. If I were to add in an additional factor, then the degrees of these numerator and denominator polynomials would be equal, and I wouldn't have an oblique asymptote. I would have a horizontal asymptote. So we're going to drop the q1 part because we don't think we need it right now, and then we're going to figure out this value of a. We're going to use the y-intercept, which is located at 0, -3. When I put 0 in, I end up with 6a divided by -2. When I put 0 into my rational function, I need to get -3 back. So -3 is equal to -3 times a. This implies that a is equal to 1. So therefore, my initial template is going to be x plus 1 times x plus 2 times x plus 3 in the numerator. And that's going to be divided by x plus 1 divided by x minus 2 in the denominator. Now, we're going to do an additional check here by seeing if any adjustments need to be made in order to get the oblique asymptote correct. So the oblique asymptote is always done by division. Okay, the remainder part of the division would get closer to 0 by definition, by the division algorithm, because the degree of the numerator would have to be less than the degree of the divisor. But when I do the division, the oblique asymptote comes from the quotient of the division. So this is what we're going to be testing. So first thing I'm going to do is I'm going to reduce this rational function down because both the numerator and denominator have x plus 1 as a factor. Remember, that's where the hole comes from. When I reduce it down, I have x squared plus 5x plus 6 divided by x minus 2. When I do the division, the quotient is going to be the oblique asymptote. The remainder, in this case, is just 20. It has no roots, so the graph cannot intersect the oblique asymptote. And as we confirm here, the oblique asymptote is indeed x plus 7. So this is our second confirmation that our format seems to be correct. So again, the division actually yields the quotient that matches our oblique asymptote. And this, again, is another check to say, hey, this template, x plus 1 times x plus 2 times x plus 3, divided by the product of the factors x plus 1 times x minus 2, seems to fit all of the information that we were able to extract from the graph. And we don't use the reduced form here because of the whole being present in the graph. We have to use the enlarged form or the form that is not reduced, so the whole is also taken care of. Now here is an example of one for you to try, where you have you have horizontal and vertical asymptotes. You have locations of specific points that you can find or that are already labeled for you. So pause the video here and see if you can figure this out. Hopefully you were able to derive this function as you went through the analysis. The function should be 2 times the product of the factors x minus 1 times x plus 3 divided by the product of the factors x minus 1 times x plus 2. Thank you for your time and attention.